In lecture 16, part 3. So in the previous part, we talked about A search already, and here we're going to extend it so that it is optimal. So remember, A search is not optimal, and I said it's because something wrong with the heuristic. So what we're going to do here is we are going to add some kind of constraint or restrictions to these heuristics and call them admissible heuristics, and combine it with A search, we get something called A star search, and indeed this is optimal and is the one that we're going to use. So first, let's talk about what is an admissible heuristic. So the definition is very simple. It's as long as we have a heuristic that's between 0 and h star, which is the actual true cost. Basically, it means as long as we are underestimating the true cost, then we're okay. So how to figure this out? Because the problem is we don't know h star, but for some of the specific problems, for some specific puzzles, we can actually figure that out. So I will give you one example of the 8 puzzle example. So for the mazes, we have seen that the Manhattan distance and the Euclidean distance, they are admissible heuristics. And here, let's talk about something similar, the 8 puzzle example. So we have an 8 puzzle, and the correct configuration is 1, 2, 3, 4, 5, 6, 7, and 8. So that's the goal state, basically. And then we have some random state S, and let's try to permute this. Let's say put 1 here, and 2 here, and 3, and 4, and 5, and 6, and 7, and maybe 8 like this. So given any state, we need to figure out some kind of approximate underestimate of the number of steps we need to get to the goal state. So let's start with the simplest possible one. Just everything is 0. Would that work? Let's check the condition. 0 needs to be larger than or equal to h, which is true, less than or equal to h star, which is also true. Because all of these needs at least 0 steps. So if we're already at the goal state, it's 0. If we're not at the goal state, we need at least 1. So, well, yes, this is admissible. Is it useful? Well, this is just not care about the heuristic. It's basically uniform cost search. So not that useful, but it's right. Let's try another one. 1. If it's 1, then most likely it's okay. But if you look at h star of g, the goal state, it's 0 because we need 0 more steps. So that's not true because 1 is not less than or equal to 0 here. So that's actually not true. So in general, for any constant heuristic, it's not correct because the goal state, usually the distance between the goal state and the goal state is 0. You only need 0 cost to, because we're already there, basically. So usually all of these constant ones are incorrect, except for the constant 0 one. Next, let's actually try some more useful ones. So here, the number of incorrect ones, number of incorrect tiles. For example, let's do it for this particular state, and it's, which ones are correct? I think only 6 is correct. So the number of incorrect ones are 7 for that particular S. Is it underestimating? I guess it needs at least 7 steps, right? It needs at least to put this 4 to this place and 1 to say that place. So at least it needs 7 steps. And if we're already at the goal state, let's see, the number of incorrect tiles is 0, so it's correct. Actually, at goal it's 0, and not at goal, it's strictly less than the number of steps because we need at least to fix those incorrect tiles, and each one needs at least 1 move. So that would be the reason we at least need that many moves to get to the goal, so it's less than or equal to the actual cost. So that's one. It may not be that good because it's underestimating these so much. So maybe let's use something that's more reasonable, and that's the sum of Manhattan distance from this tile to the goal. From each tile to the correct position, basically. Okay, so let's see, for example, for this one, the Manhattan distance from 4 to this 4 is 1. The Manhattan distance from this 8 to this 8 is 2. And 2 is 1. And 5 is 1. And 1 is 2. And 6 is 0. And 7 is 1. And 3. 3 is here. And it needs to go up, so 2, and last 7 is 1. So that's the sum of the Manhattan distance between each of these tiles and the correct position. So if you use this, it's actually always underestimating. First, if we are already at the goal state, the distance will be 0 because all of these distances are 0. If we are not, then 4 needs at least to move one step to get to 5. No matter what happens, it always needs at least 1 because it's a Manhattan distance of 1, so it needs to move one step. And similarly, 8 needs to move at least 2 to get to that position. Usually we will not be able to do that, but that's the least number of steps it needs to take in order to get to the correct position. And similarly, with this 2, so the 1 here, it needs at least 2 steps. So the Euclidean distance is actually smaller than this, so it's okay too, but the Manhattan distance is basically a better one. And the important property is always it satisfies the condition that we're underestimating the number of steps that we need. Okay, so we will have more examples again in the Canvas lecture. And let's talk about which heuristics are better than other heuristics. Like in the previous example, I talked about the Manhattan distance is better because a better heuristic has larger values, but it's still smaller than the actual cost. So here, 2 is better than 1. So what we say is 2 dominates 1. So this should be dominates. And it means it's better and it will be faster compared to using a better or a heuristic that dominates another will mean the A star will be faster and more efficient. So that's the idea. So we want to, given a particular problem, we want to choose the cost that's basically as close to the true cost as possible. And of course, we talk about the problem with A search. It's not optimal because sometimes the heuristic would overestimate the true cost. But if we are okay with non-optimality, then we prefer the heuristic is kind of close to the actual cost, but may overestimate the cost sometimes. If we don't care about the optimality, we just needs it to be very fast. Because the closer we get to the actual cost, the faster the algorithm. In general, not in every case. So that's again a summary. So A star is basically the same as A, so there's nothing new at all, and it's just we're using a admissible heuristic, so the heuristic is different. So as I said, A star is complete and optimal, and we can expand this and combine the iterative deepening idea with A star. This is actually not often used, but the idea is the same as IDS with DFS. So we're basically replacing DFS by A star, and we're going to check everything with cost less than 1, less than 2, and until less than D. So we're basically, in the first D steps, we're searching for the actual distance between the initial state and the goal state, and at the end we will reach that goal state. at some level D. So of course it's still complete and optimal, and usually it's more costly. Not always, but usually it's more costly, so often we don't use it. So for uninformed search, we often use IDS, but for informed search, we often just use A star. And there is yet another variation called the beam search. So it's kind of the idea of DFS to save some space, but the way we save space is we're going to just limit the length of the priority queue to a fixed size, say k. So after k, so only the top k are capped at each time. So the very large cost one, the states with very large cost will be removed. So the storage is kind of the space complexity is smaller. And there are two ways of doing this. One is fixing the size, and the other one is fixing the total cost. So the cost is larger than something, then we get rid of those. And that limit is called beam width. And as you can guess, we're removing stuff, so obviously it's not going to be complete and not going to be optimal, although it saves space. So that's why it's often not used as well. So basically, A star is the go-to algorithm for informed search.